करते हैं ना ठीक ठाक क्या चीज था
ഹലോ ഓഡിബിൾ അല്ലേ?
അതെ മാം.
Good evening, all. We can start the session now. A small request to the participants in case of any technical difficulties, audio video issues, or connectivity problems during the session, kindly communicate through the official FDP WhatsApp group, and our organizing team will assist you promptly. Respected dignitaries, esteemed resource persons, respected principals, faculty members, research scholars, and dear participants. A very good evening to all of you. As a part of AICT Atal sponsored faculty development program on disaster management and resilient infrastructure, it will give me immense pleasure to introduce our distinguished resource person for today's session on generative design for climate resilient planning, Ms. Anu Vivi. She is a system researcher at the Global Climate Forum, Berlin, Germany, working in the area of green growth with a strong focus on climate risk management, sustainability analytics, and system-based approaches to effective climate policy. Her research contributions include studies on urban water systems, European forests, climate biodiversity interactions, and resilience to extreme weather events, which are highly relevant to disaster risk reduction and climate resilient infrastructure planning. She holds a master's degree in civil systems engineering from TU Berlin and has a strong academic foundation in geotechnical engineering from IIT Kharagpur. Ms. Anu, accomplished researcher and a speaker with several papers accepted and under reputed international journals and conferences. He has also delivered invited talks at international forums, including IKIP 2025, where she addressed critical aspects of climate change, ecosystems, and resilience. We are truly honored to have her share her insights with us today. The session is scheduled from 6 p.m. to 7:30 p.m., and we kindly request all the participants to remain present for the entire duration to gain maximum benefit from this session. On behalf of Organizing Committee and IAS College of Engineering, I extend warm welcome to Ms. Anu Vivi and invite her to kindly take over the session. Thank you.
Thank you, ma'am. Can I share the PPT right now?
Yes, ma'am.
Is it visible?
Yes, ma'am.
Okay. Should I switch to the other mode? No, all this is okay, right? Rather than the complete, slideshow, that's okay?
Slideshow.
Yes, slideshow. Okay.
Screen, please, ma'am.
Yeah, thank you. So as stated by ma'am itself, like I'm Anu Velaiden, basically a climate researcher in Berlin, and I do have a background in civil engineering and geotechnical engineering, but due to some passion in climate and sustainability, I have switched my career from a civil engineering perspective to basically into the climate related projects. So dealing with some EU related projects currently. So on this very particular occasion, good evening, everyone. I would like to take this opportunity to express my sincere gratitude to the FDP team of IES Engineering College, Chittilapalli Thrissur, for providing me with this wonderful platform to share insights on the important theme of disaster management and resilient infrastructure. My heartfelt thanks to Dr. Brilli Sankita, Principal IES Engineering College, for her leadership, and Ms. Anju EM, HOD of department, head of the department, that is Civil Engineering, IES Engineering College, for her constant support and coordination. I would also like to extend my appreciation to Ms. Steffi, Ms. Asha, and Ms. Bhima, Assistant Professors of IES Engineering College, for their valuable efforts in organizing and facilitating this program. I'm truly grateful for the opportunity to engage with such a wonderful academic community, and I sincerely hope that the discussions and the ideas shared today will contribute meaningfully to building safer, more resilient communities. So before I commence into my actual topic, let me start with the real name of the FTP, that is Disaster Management and Resilient Infrastructure. So why do you think that disaster management or resilient structures are so important? They're basically, or why is it so important in our own country as such? There are a few points to highlight, especially there is high exposure to multiple hazards. Our country are prone to different multiple hazards like floods, cyclones, landslides, heat waves, and even the second important point is like rapid urbanization and informal settlements, which basically happens only due to the population explosion. And the third highlighted point is climate change intensifying disasters. And fourth, economic stability and development, protection of vulnerable communities, which is like low income people. So if we elaborate on all those areas, what I could say is like, in regard with high exposure to multiple hazards, our country faces frequent natural hazards, such as I stated earlier, floods, cyclones, earthquakes, heat waves, landslides, and urban flooding. Poorly planned infrastructure increases vulnerability and leads to large-scale human and economic values. And in regard with the rapid urbanization, as it's often stated, like it's because of the population explosion, fast, often unplanned urban growth results in encroachment on floodplains and the wetlands, and also due to the high number of intrusion into the cities or the population being migrating into the cities, we need to provide lots of drainage systems. That is, even inadequate drainage systems sometimes pose a threat onto the cities. And thirdly, unsafe housing in high-risk zones, especially the seismic-prone areas. So resilient urban planning helps reduce disaster risk before even they occur. And the third important point is like climate change intensifying disasters. As we all are aware, this climate change is like a global catastrophe or global issue. So climate change is increasing the frequency and intensity of extreme events like longer heat waves, intense rainfall, rising sea levels, and stronger storms. So infrastructure designed without infrastructure designed without climate resilience fail under these stresses. And the fourth important point is economic stability and development, where disasters basically cause massive damage to roads, bridges, power systems, water supply, and housing. So investing in resilience means it saves lives, reduce long-term recovery cost, protects national development gains. It has been stated that every dollar invested in disaster risk reduction basically saves up to $7 in disaster recovery. And the fourth, and not the fourth, rather the final important point in relation with the importance of this aspect, disaster management, is protection of vulnerable communities, where low-income populations are often the most affected to unsafe housing and limited access to services. So resilient infrastructure basically promotes equity, safety, and social stability. Moving on to my topic, basically it's generative design for climate resilient urban planning. So it is a topic wherein I would like to bring forth some software solutions that can be used in order for urban planning. But beforehand, I would like to have an interactive session with you all, wherein I would like to know the designing softwares that are used within our own country for designing the infrastructures which you are currently aware of. So for this question, could you answer the softwares that are known to you for designing infrastructure in the chats as possible? Since I know all are like mostly faculties related to with civil engineering, I mean, totally in civil engineering field. So what could all be the softwares that we know in regard? Yeah, AutoCAD, ETAP, StatPro, yeah. In yeah, SAP, yeah, Revit, BIM. Is there any other software? Yeah, Tekla, Safe, yeah. Slide 6. 3D Max, Stat Pro, ETAPS, yeah. Stat Pros are basically the designing softwares here. And in relation with if a complex structure has to be generated, then a very highly complex structure has to be generated, but we need
Anyways,
to, yeah.
anyways,
Yeah.
sorry for the interruption. Ma'am, full screen.
Full, no, I am not talking about any slide. I'm
Okay.
talking in regard with this
Okay, ma'am.
software. So I just wanted to know whether out of the softwares, not out of this, rather, is there any software which you are aware of where you could just implant more parameters like climatic effects and then generate innumerous solutions at with very limited time? So are you all aware of any software other than the Revit, ETAB, STAD, and even for foundation analysis, Plaxis also is quite important. But I just wanted to know is are you all aware? Yeah, FEM is their finite element method. Yeah, tool. So Plaxis is one among the finite element tool too, I guess. Answers. Okay. Thanks for all the feedbacks. I mean, all the answers that I've got. So I think I have to really move on to the topic, because this topic is going to deal with the softwares, which is completely far away from what do you call AutoCAD, Revit, StatPro, or SAFE, etc. So this is a topic is related with the generative design for climate resilient urban planning. Now, why did I choose this particular topic, that is generative design for climate resilient planning? Way back while I was studying over my bachelor's and my master's in India, I was only aware of these particular softwares which I've currently quoted. But during my second master's in TU Berlin, I was I confronted a new paradigm, or like a software which could provide me with innumerous solutions wherein you are not using any sort of drawing mechanism. You're not using in AutoCAD, as you give the command line, what do you say, rectangle, circle. You're not providing any commands. Rather, you are using some tabs wherein each tabs are embedded with algorithms, and then you are linking together, and then you are generating a layout. So when I was pursuing my TU Berlin course, what I have seen is like we had numerous course modules related with this particular generative design softwares or parametric modeling softwares, which in fact led me to choose my master thesis in the topic related with parametrically designed energy efficient skyscrapers transforming Berlin's modern perspective, where I was able to generate a complete skyscraper structure with innumerous design solutions, along with implementing a lot of climatic aspects into it, so that I could learn the sunlight effect, wind analysis effect, so that I can place solar cells, wind generating small turbines, and even daylight analysis, shadow analysis. All this could be done in this particular sort of software. So I was when I was told about carrying out FDP over here, I thought, why not introduce the generative design or the parametric modeling related softwares, so that all are aware about this new methods or technology adopted abroad too. So moving on, the importance of disaster management. Basically, generative design uses algorithms, simulations, and data. Data, if I say it's like climate, hazard, population, infrastructural data, to generate and evaluate an urban planning solution. And it is not a single solution. If you urge for a single solution, it will provide a single solution. But if you need a multiple solution, then it will definitely give you multiple urban planning solutions. In disaster management, this approach is extremely valuable because it helps anticipate the risk at a very far forefront, test various test case scenarios, design resilience even before the disaster even occur. And thus, rather than reacting afterward, we have what management, disaster management application can be applied just with the aid of generative design. Now, why generative design is important for disaster management? There are a few important factors for it, especially proactive risk reduction, scenario-based planning for extreme events, optimization of critical infrastructure, and climate change adaptation. If I take into consideration the proactive risk reduction, which means the generative design allows planners to simulate floods, heat waves, cyclones, earthquakes, and sea level rise under different climatic scenarios. This helps identify vulnerable zones very early and design cities that minimize the exposure as well as the damage. That is basically termed as a proactive risk reduction. Second one is scenario-based planning for extreme event. That is, instead of one static master plan, which means it is a traditional methodology being applied, instead of one static master plan, generative design creates hundreds of alternatives, testing how urban layouts perform during the disasters. So cities then choose solutions that remain functional even during the extreme events. And the third one is optimization of critical infrastructure, which means it helps to optimize the placement as well as the design of roads, evacuation routes, hospitals and emergency shelters, and even drainage and flood control systems. This basically ensures faster emergency response and reduce system failure even during the disasters. And the last one is the climate change adaptation, wherein as climate risk evolve, generative design basically integrates future climatic projections. That means if you're taking into consideration a particular place like Bangalore, you're taking into consideration, you have the weather data over that place. And if you're designing a building over there, then you can, in fact, collect all the weather data related with the Bangalore for around 10, 20, 30, or 40 years, and then have a ultimate projection, future climate projection done. And then you can impart that into the generative design softwares and do the analysis. So you have a futuristic projection of even the designs, how the design will react during different years. Into thus the future climate projections into planning, enabling long-term resilience against intensifying disasters. So basically, the disasters that are occurring totally are not natural, but poorly planned cities make them very disastrous. Therefore, generative design enables cities to plan for uncertainty, complexity, and climate extremes. Now, the total PPT or the total session for today has been divided into four separate sections too. That is, first, I will be dealing with the rethinking urban futures. That means why climate resilience matters. Second one, generative design, a new planning paradigm. Third is the tools and technology that is completely based on the softwares for climate resilient design. Fourth one is applying generative design for real urban solutions. So moving on to the first part, that is rethinking urban futures and why the climate resilient indeed matters. If you take into consideration the climate changes within the cities, if you take India or any of the countries around and the cities where, and also take into example the cases of cities, even the climatic change do have some sort of impacts on the cities. If we are urban planners, if we are architects, if we are civil engineers too. So of course, this climate change do have an impact on the design aspects of the infrastructure that we are planning. So the key points related with the climate change challenges in cities are rising temperatures and heat waves, increased flood frequency, coastal risk and sea level rise, stronger storms, and extreme rainfall. So if I take into consideration the rising temperature and extreme rainfall, okay. In regard with the rising temperature and extreme rainfall, heat waves, one of the most visible impacts of climate change in cities is the sharp increase in the temperature and the increasing frequency of the heat waves. Urban areas suffer from the urban heat island effect, which is quite important for the civil engineers, which means where concrete, asphalt, and buildings absorb and retain the heat, making cities significantly warmer than the surrounding regions. So if I quote an example, Europe's 2022 heat wave broke temperature records across multiple cities. Paris, Madrid, Rome recorded temperatures above 40 degrees Celsius, leading to thousands of excess deaths. So according to studies published after the event, urban neighborhoods with limited green space were disproportionately affected. Similarly, in India, that is in 2023 heat wave, severely impacted cities like Delhi and Ahmedabad, disrupting electrical supply, increasing water scarcity, and forcing schools and construction sites to shut down. These events, basically what they highlight are rising urban temperatures are not just a comfort issue, they are a public health emergency, increasing heat stress, respiratory illness, and mortality in total. Now, moving on to the next slide, that is the second factor, second climatic change is increased flood frequency, wherein another major challenge in cities, what the cities face is the growing frequency and the intensity of urban flooding, driven by extreme rainfall events and inadequate drainage infrastructure. So a recent example is 2021 floods that is in EU, that's in Germany and Belgium, where intense rainfall overwhelmed urban drainage systems, causing catastrophic damage in cities such as Cologne and Liege. Despite being developed regions, the floods resulted in 200 fatalities and billions of euros in losses. Similarly, Bangalore in India experienced repeated urban flooding in 2022 and 23, even after moderate rainfall. Rapid urbanization, loss of wetlands, and encroachment on natural drainage systems channels have made the city extremely vulnerable. These floods disrupted IT hubs, transport systems, and residential areas, showing how climate risk intersect with the planning failures. Urban flooding today is not a natural hazard as such, but also a planning and a governance challenge. And the third important climatic challenge is coastal risk and sea level rise. So coastal cities face a unique and escalating threat from sea level rise and coastal erosion. As global sea level rise, cities located near coastal lines are increasingly exposed to flooding, saltwater intrusion, and infrastructural damage. For instance, Jakarta, one of the fastest sinking cities in the world, experienced frequent tidal flooding that affects roads, housing, and water supply. The Indonesian government basically has decided to relocate its capital due to the long-term climatic risk too. Similarly, cities like Miami experience sunny day flooding, where seawater floods streets even without rainfall, caused solely by the rising sea levels. These examples basically underline that coastal risks are not distant future scenarios. They are already shaping urban relocation, infrastructure investment, and long-term planning decisions. And the fourth important point is related with the stronger storms and extreme rainfall. where the climate climate change is also intensifying the storms and extreme rainfalls, increasing damage to urban infrastructure and essential services. The 2023 Mediterranean storms impacted cities in Italy, Greece, Spain, causing flash floods, landslides, and power outages. In many cases, the transportation systems even collapsed, hospitals faced disruptions, and emergency services were overwhelmed. So in the United States, in Hurricane Ian, that is in 2022, severely affected cities in Florida, demonstrating how stronger storms can devastate the urban housing, energy systems, and coastal infrastructure within hours. So such extreme events reveal how tightly interconnected urban systems are basically, and when one system fails, others quickly follow. Moving on to the urban vulnerabilities, as stated in the previous slides about the urban vulnerabilities, basically the urban heat island effect, where we have the asphalt, concrete, which takes up all the heat and then completely makes up the infrastructure warm, which can be termed, or the infrastructure or the location completely, it makes the cities completely warm, which can also be stated as urban heat island effect. Then in regard with overpopulation, then it leads to overloaded drainage systems, then dense infrastructure and limited green space, which is also an current urban vulnerability, and social vulnerability and inequality related with the low-income people. So these vulnerabilities within cities are rooted in how they are designed. So materials like asphalt and concrete absorb heat, making cities significantly warmer than the surrounding rural areas. A phenomenon known as the urban heat island effect. This increases cooling demands and as well as energy cost. So moreover, the flooding, which becomes severe when impermeable surfaces prevent water from infiltrating the ground, the stormwater systems designed decades ago cannot cope with today's extreme rainfall intensities. Many neighborhoods lack green spaces that could act as natural cooling and flood mitigating systems too. So social inequalities even deepen the climate vulnerability. Low-income communities often live in areas with poor infrastructure, limited access to cooling, and inadequate housing conditions. The climate resilience must therefore address not just environmental risk, but also the equity dimensions within the cities. And therein, we need for new planning approaches, which highlights some features like urban systems becoming more complex. And traditional plannings are still too slow, and there are need for data-driven decisions. And we also need to, in current scenario, we really need to integrate some climate modeling into the designing and the planning scenarios. So the pace and the scale of climate change demand more faster and more adaptive planning methods. Traditional planning approaches, often manual, sequential, and based on limited data sets, are not sufficient for today's challenges. Cities now require planning frameworks that can integrate big data, real-time environmental models, and future climate projections. So planners need tools that can simulate outcomes before implementation, helping them choose the best options. So this includes making decisions about land use, green infrastructure, building placement, and mobility systems while considering the climatic hazards. So a new approach must be dynamic, iterative, and grounded as well as in evidence. So moving on to the limitations that are pertaining to the traditional urban plannings are basically, it relies on the static master plans, and it has limited scenario testings. Because innumerous design solutions are not possible, it is a time-consuming process in the case of traditional methodology. And moreover, human biases in design. Of course, if many humans are in the designing process, of course, there can be biases, clashes, etc. So, coming up with a fraud-friend solution is quite difficult. And it's also a time-consuming process. So the traditional urban planning relies heavily on static master plans that assume predictable futures. These methods do not allow cities to explore multiple design options rapidly, so limiting the planner's ability to test how different scenarios perform under climate stresses. And human decision making, while essential, can introduce biases or overlook potential solutions due to time pressure or analytical constraints. Manual design processes are slow and often cannot evaluate thousands of variables continuously, which is like a very big limitation of this traditional method. As climate change accelerates, cities require planning tools that can handle complexity, provide robust alternatives, and support better long-term decisions. This basically brings us to the generative design. So moving on to the second session, that is generative design, a new planning paradigm. As I have stated early in my onset of the PPT itself, this generative design is not a platform where you are developing our design with the aid of some icons. It is basically, we are using some tabs wherein embedded coding systems are available. So until or unless you know what are the coding systems or what are the tabs to be used, it's a little bit, tedious process. But if we are able to learn this mechanism, then a huge number of design solutions is possible within no time. So basically, this generative design is an algorithmic design, driven design. And we need to provide some rules and constraints and objectives. That is, if you're giving some dimensions, whatever dimension it be, whether it's a numerical value, you are providing in the form of a tab, small tabs. And each tabs, I will show you the picture in relation with this scenario which I'm telling you. So it's like small tabs are used, and each tabs are basically connected with wires. So all the parameters, all the construction constraints, all the objects, all the rules are fed into it as what do you say, in the form of tabs which have some algorithmic content in it. And when you do the analysis, generates thousands of solutions and helps, and even allow us to find one single solution, or just we can go for a best fit model optimization of the solutions. Now, moving on to how algorithm-driven solutions work. So it basically follows some computational modeling, environmental performance scoring, optimization loop is there, and rapid scenario generation is there, which means generative design relies on computational simulations that test each variation of the design. Algorithms evaluate the performance of each scenario using metrics such as wind flow, sun exposure, shading, flood mitigation potential, walkability, and carbon emissions. So the system that runs the optimization loops, similar to natural selection done by a human, identifying the best performing solutions and refining them. This iterative approach allows designs to evolve based on the performance. So thousands of simulations that would traditionally take months can now be completed in hours. For climate resilient planning, this capability is very invaluable. Moving on to the next segment that is related with the parametric tools and the digital parametric tools and the digital twins. So we have software which is known as for parametric modeling, that is for designing purpose. We have the software known as the Grasshopper and the Dynamo. And one among the software is actually inbuilt in the Rivet 2. And then we have a term which is like digital twin technology, which is like you can build a 3D model with all the real-time parameters being embedded into that. And then you have the real-time monitoring and the feedback system. Data integration from different sensors are also possible into these parametric modeling tools. So as a whole, parametric modeling tools, basically this Grasshopper or the Dynamo, allow designers to create flexible models that automatically update when parameters change. So this means Planners can instantly visualize how adjusting building density or green space affects temperature or flood risk. While digital twins go one step further, creating virtual representations of entire cities using real-time environmental data. And this allows planners to monitor urban systems, run simulations, and test future scenarios with unprecedented accuracy. Together with parametric tools and digital twins provide a powerful foundation for a climate resilient design as such. So, what are the advantages of, one second, yeah. Okay. What are the advantages related with the parametric design over the conventional methods? So advantages are basically the designing is very much faster. If design cycles are there, then it's faster comparatively compared with the traditional methods. And even decision making is also faster. Evidence related decision making can be implemented. And even it reduces risk as well as a cost, and it does have a greater innovation potential. So the generative design offers major advantages over the traditional ones. So it accelerates design cycles, helping cities respond to climate threats more quickly. Designs are no longer based solely on the experience or intuition, but rather supported by quantifiable environmental evidence. So exploring thousands of alternatives reduces the risk of poor decisions and optimizes urban performance. This can lead to cost savings, both in construction and long-term maintenance as such. So most importantly, the generative design encourages innovation by revealing unconventional solutions that still meet all the planning criteria. Now, moving on to the next aspect, which is like beforehand, yeah. So in the next slide, I'm showing you the complete, in order to generate a structural column. So this is the interface wherein you work rather than using, in AutoCAD, might be you have seen the interface is where you are providing with the lines, joining it, etc. But over here, you are basically using some tabs. You can see a complete network, and where you can see different boundary offset in the first position, second position, we have a structural columns. You can provide the number of columns over there. Then you have some principal vectors and combinations, like where you actually, where in which coordinates you really require the structural columns. And you have the view names, that is if you need a front view, elevation, what do you say, top view or side view, whatever views are required, you can feed in the view. Then you have the element subsets, like how many elements are to be provided. Then you have the view central point auxiliary, view center point, where you actually place a center point of the complete structural thing. Even though this network is a little bit complicated, but once it is learned, that means even in a numerous structural column with, what do you say, if you need to change the parameters and test the structural columns or generate the structural columns, it's quite possible. And if you do want to do the analysis, you can just provide what sort of analysis you require for structural columns. You can provide different tab segments, and even you can visualize in the form of some plots or what do you say, diagrams. This is another example of a complete structure generated with the aid of Grasshopper. This is a complete structure generated with the aid of Grasshopper and Dynamo. So where you have arches built in with a loss of element, a complete structure, I mean truss elements. Even you might see that in one side of the portion, you can see a complete network is available. It is a complex process. It's not a very easy process, but once it's learned, it's pretty easy to generate even highly complex structures. Or if you want to change the design of the structures, or if you want to change the dimensions, if you want to change the properties of the structure, it's also quite possible. And this is another form of an example where it's like the truss developed with the aid of Grasshopper Dynamo. And then moving on to another columns or tower, where It's like a complete element with beams and columns, or with it's a sort of a tower generated with the aid of Grasshopper, where basically when you are creating the layout, it will only be a line segment, and the other things will be generated only after the complete evaluation or the complete designing process. Now, this is about the skyscrapers. So if you are just generating if you are just creating only one particular rayon, for example, if you're only creating this under portion, sorry, one second. The bottom portion, if you could see where I'm pointing it out, if you're creating only that particular layout, the entire structure will be generated with the aid of all the this grasshopper dynamo mechanism, while by building the network or the algorithm, the aid of use of algorithms and implementing all the parameters and constraints and data, you could just even change the shapes also. So only the bottom portion you need to draw, the rest entire structure can be generated at one go. So these are 3 designs of skyscrapers generated with the aid of a dynamo. And some AI stuffs are also used wherein you can give some forms, the facade forms for this skyscraper structures. Then this is not pretty clear diagram, I know that, but I just wanted to tell you that in order to create a skyscraper, you can go for innumerous solutions. So on the right side, you can see small innumerous circles. So it's like by just changing the angle inclinations or some parameters, some different design solutions are being generated. So this is how, with the aid of Grasshopper or Dynamo, this is how you could generate innumerous solutions at one go. Now, moving to the tools and technology for climate resilient buildings. So as stated, what we use is Rhino Grasshopper. And we have ArcGIS also. It's like a 3D modeling software. Even Autodesk related generative design is also possible. And within the Rhino and the Grasshopper, we have some inbuilt icons like ladybug, dragonfly, where we can use, we can just do some analysis like solar radiation analysis. We can use wind analysis, daylight analysis, shadow analysis, etc. can be done. So basically the last one, that is ladybug and dragonfly, are some plugins associated with the Grasshopper Rhino. So the several software tools support a generate design for climate resilient planning. Basically, the Rhino and Grasshopper are popular for parametric modeling and enable environment simulation using plugins like Ladybug and Dragonfly. And the case of ArcGIS, Urban allows, it allows spatial analysis, 3D modeling, zoning simulations, and future growth scenarios. And the third one, the Autodesk Generative Design tool, basically specialize in automatically generating optimized layouts. So when combined with a Rivet, these tools allow planners to simulate building performance in relation to climate hazards. So each tool has its own strengths, and often multiple tools are integrated in a sequential workflow way. So when multiple tools are incorporated and data being transferred, or some files are being transferred, it turns out to be an integrated collaborative system. Now, moving on to the software installation uploads. You can download this Rhino from McNeil website and just install it. And when you provide a command of Grasshopper inside that, then another interface opens. It is like a Windows scripting bar, which is termed as a Grasshopper. And if you need to do some, analysis, which I stated earlier, like shadow analysis, light analysis, sunlight analysis, radiation analysis, wind analysis, etc., then you could use the Ladybug tools, which also which also could be downloaded. Each icons could be downloaded, and it can be used. It gets into as an icon within the Grasshopper itself. Then some other icons basically are Galapagos, Octopus, and Balasai, which in Galapagos, it's like a single constraint you can change. While in Octopus, it's like multiple constraints could be changed. And Balasai basically gives a visualization. And in Valisai, it also where if you're doing it like one parameter, you're making it constant, other you're changing, you could see the various visualizations, or you could generate graphs, or you can study the analysis portion with the aid of Valisai. And if supposedly, for example, you are taking into consideration design in Delhi, and you need to impart, you need to know about the structural performance over there, based in Delhi, based upon the climatic or the weather data, then you could implant all the climatic data through GIS into this rhino and grasshopper. And moving on to the real world features. So I stated just some time ago regarding the solar radiation analysis we could perform. Even flood modeling can be done. Wind simulations and even some optimization dashboards can be created, which means like these tools provide advanced features essential for climate resilience. So solar radiation analysis help planners identify areas prone to overheating and opportunities for shading or green roofs. Then flood modeling basically predicts water accumulation zones, enabling better placement of stormwater infrastructure. And in regard with the wind simulations, it basically evaluates the ventilation corridors, improving cooling across neighborhoods. And optimization dashboards, which means like it allows planners to compare multiple scenarios, showing performance metrics side by side. And these capabilities allow cities to base decisions on precise environmental evidence. Now, moving on to the workflow, how does the workflow happens up? It's like a typical workflow begins with importing the GIS data, such as elevations, land use maps, and building footprints. Then the designers basically create a term, that is a model known as parametric model, defined with climate-related constraints, such as minimizing the heat or maintaining flood buffers. And the generative design engine then produces multiple scenarios and evaluates them. So users can interactively adjust parameters and rerun simulations to refine the results. So ultimately, basically, the planners receive a narrow set of optimized solutions with performance goals. So this workflow ensures that the climate impact is embedded from the earliest design stages itself. Now, in order for that, in regard with the user and the data requirements, of course, since you have seen the network, it is a complex network, then you need really require a skilled operator or engineer, which can deal with algorithms, Python coding, or how the networks could be totally generated. It all relies on the hands of the skilled operator. And the second data requirement would be the climatic data sets, such as the reliable climate data sets like rainfall projection, temperature records, and hazard maps are essential for accurate simulations. And the very most important point is high computational power. That means because generative cycles involve thousands of computations, high performance computing devices may be required. Finally, stakeholder involvement is crucial, because a generative design solution must reflect community priorities and economic constraint and policy requirements also. Now, I'm moving to the fourth slide, that is applying generative design or real urban solutions. That is the fourth section, wherein I'll be dealing with the main segment, that is cooling street, where you use the generative system for urban planning, where if at all in a design we have to implant some cooling streets, then it's like you need to provide some shaded pathways, wind corridor enhancement, or some reflective materials, and some green infrastructure. So all this could be actually implanted to the generative design itself. So it has been used to reduce urban heat by optimizing street orientations, identifying ideal location for trees, and maximizing the shading. And these algorithms basically test thousands of configurations to find designs that improve wind flow and reduce surface temperature. Combined with cool materials and vegetation, streets become significantly more livable during the heat waves. And in regard with the flood, which is like most important factor if we take our own country, managing flood, that means within the generative system, we could create some sponge strategies, some detention basins could be implanted, permeable surface could be used, or nature-based solution can also be used. So in flood-prone areas, the generative designs basically helps model water flow patterns and surface permeability as such. So planners can identify optimal placements for wetlands, biowhales, and retention ponds in general. So algorithms can redesign urban layouts to create natural drainage paths and reduce runoff loads. This leads to resilient nature-based systems that perform better than the concrete-only solutions. Now, moving on to green infrastructure expansion, it's like you can provide green roofs of facades, even some biodiversity corridors could be used, multifunctional parks can be accommodated, and even air quality benefit analysis can also be carried out. That means the generative tools test the capacity of different green strategies to cool the city, absorb stormwater, and improve the biodiversity. So planners can explore alternative green roof placements or design new parks that serve both recreation and climate mitigation processes. So this leads to multifunctional landscapes that support ecosystem services and improve well-being. Now, based on the scenario simulations and decision support, where we have in the generating system itself, we have multiple scenario comparison. That means if lots of design solutions are generated, we can make a comparison. We can go for trade-off visualization, even climate stress testing can be done, and data-informed policy decisions can also be accommodated, which means basically generated design excels in scenario planning. Cities can compare low density and high density models, car-free zones versus mixed mobility strategies, and assess how each perform under climatic stresses can be also carried out. So interactive tools allow decision makers to see trade-off clearly, such as heat reduction versus cost, and make policies grounded in the data. Now, moving on to the case study, this I have included. I'm not going deep into the case study part because I just wanted to, since it's a complex mechanism, the generative design and the parametric modeling is a very complex system. So I'm just quoting two papers related with the generative design of the urban planning. And then I will be showing some, figures related with that. So the first paper is related with climate response urban planning through generative models, sensitivity analysis of urban planning, and design parameters for urban heat island in Singapore residential settlements. In this paper, basically, in this, if you focus on this diagram, you could see that three aspects are taken into consideration, especially on the right-hand side. Architectural design, that means it is inclusive of the building form, construction material, glazing design, facade design, and building systems are basically the parameters which are related with architectural design. So when you are completely planning the infrastructure or the building assets, you are providing these parameters into the grasshopper or the dynamo. And then you have the urban design, wherein you provide the building height requirement that is possible, the green plot ratio, side coverage ratio, tree coverage ratio, street canopy, and land cover material. So it's not highly requisite that you have to provide all the parameters as such. Whatever you feel like is useful, you could use it for the design purpose. And the third one is urban planning, where you do the parcelization. That means each area is segmented, and land use is also provided as a parameter. Then you have the road network, street orientation, gross plot ratio. All these are actually given as some tabs which are interlinked with each other. Thus, it will be like a huge network, a cumbersome network indeed. Now, so while the process for this paper publication, it's like for this urban planning designing in Singapore, basically the site selection is done based upon the climatic scenario too. Then the generative modeling, where the site, greenery, and the buildings are totally taken into consideration, and some parameters are imparted. The parameters that I have just mentioned earlier, those are the parameters imparted. And then simulations are performed under different daylight conditions, different day conditions, like you have the day, night, or if you want the annual condition, then different simulations are performed. And thus the result that obtained, it can be for a showcase in the form of some graphs or correlation analysis or sensitivity analysis. And the design evaluation actually it provides you a best fit solution. So if numerous designs are there created, then it provides you a best fit solutions. I'm not totally going into deep of this particular paper. I just want to give a crisp, very brief of the mechanism adopted in Grasshopper. So this is actually on left side, you could see the master plan, which is like some other software drone master plan. On the right side, it's a generated master plan with the aid of the Grasshopper. And where you could see all the building stuffs, all the residential areas and grass, every thing that is being seen in urban planning segments are incorporated, and even the asphalt road. So when you're providing the asphalt road also, you are giving all the parameters required for that. Then moving on to the next slide, that is you could see on the left side, you could see the inputs generally given for the site sections. As I have mentioned earlier, road category, road network, site boundaries, road density, all are provided for the site specifications, even the parcel size. And then in greenery sections, we are providing only the park location and park radiuses, where the parking facility needs to be provided. And then you have the building parameter section, wherein you give the building footprint, target building numbers, how many buildings has to be accommodated, then space specifying multiplier, gross plot ratio, height control, setback control, all are the inputs which are required. No, it's not like we have to stick on to this complete input as such, but based on our own choice, we could provide the parameters or the inputs. And thus the complete analysis would be carried out. And there you could see on the right hand side some plugins basically used as Ladybug, Dragon, and all. So with the aid of that, environmental analysis are carried out, and then you get the 3 outputs, which are different in nature. The 3 of the outputs are not unique, they are different. And it's being stated that 21,000 models are generated after the complete simulation. And this is just a diagram where it showed how different possible solutions could generate up. And if you need to check with the parcel area, then 3 solutions are generated. Road density also, how much road density or how much road network is possible, it based on the percentage not percentage allocated, rather this percentage are solutions or answer or analysis outputs. And then park location, how much, where would be the location of the parking area, park radius, free coverage system, building density, podium density, etc. So for each of the things, each of the output parameter, we are, it's being shown that at least three of the solutions are being shown or portrayed. Then moving on to this slide, this I have kept just because I just wanted to show that even on the top portion, you could see the, correlation analysis that could be done with among different parameters. So even a visual representation is possible with the aid of Grasshopper and Dynamo. Then next is about a case study, which is generative urban design for smart, sustainable, resilient cities, wherein the same mechanism is adopted, that is in that particular region, that is in the sustainable resilient cities, mainly industrial component has to be generated too. So industrial component has been created. Then you have the building, building designs are also incorporated, and the complete city as such, or the portion of the city where you have to design it, are also taken into consideration. And then they are provided as data with a lot of constraints, requirements, and goal values. And then it undergoes, it basically creates a parametric model. It undergoes the generation. And if whatever design, if you have some design goals related with urban designing, design goals are set. And if at all, supposedly you need to change different parameters, you could change the parameters. That means again, an optimization or an evolution is happening up. So it is turning out as a loop over here, and then a final best fit model is generated. So this is just a traditional method model. This is a SpaceMaker software wherein a traditional method modeling is shown. While in the case of generative design, you could see underneath that different forms of solutions could be generated. So it's not one single solution, different forms of urban infrastructure placements are shown underneath. And then this is again a generative design method model itself. And then this is a visualization of building and parking configuration. So all the yellow parts are basically the buildings. And if at all parking space has to be allotted, it will be given in different design solutions possible. It's currently only two design solutions are there for building and parking configuration, but numerous can be generated based on different building placements, based on different building shapes. And this is rated with a solar PV or energy radiation analysis, where in both of the figures, so wherever there is the density of blue color is higher, that means there the energy, solar energy is comparatively higher. Wherever it is lower, that means it is in light blue colors. So this sort of analysis also could be created within this grasshopper dynamo segments. And this is about daylight analysis, wherever the green intensities, green color is higher, that means there the daylight factor is higher. And as the intensity reduces, it turns out into light mode. Now, the challenges that is basically pertaining to those grasshopper or the parametric modeling or the generative designs are basically data uncertainty. That means in case, since it is a cumbersome or a complex methodology, so what all data are required, it is like it poses a confusion. So what all data need to be accurately taken. So that is a limitation. Then you have the model complexity. Since innumerous, thousands of solutions, 10,000 to 20,000 solutions are generated. So it's just a complex scenario. But even though the grasshopper and dynamo itself predicts us a best fit model. So that is the best advantage of it. But it is a little bit complex, as again, you could see the network is also huge. Then stakeholder acceptance, because we as the designers or the clients as the people who really require the designs will have some sort of challenges or some sort of requirements. Those people won't be able to even understand some of the the design perspectives, but until and unless being discussed or being explained by a professional who does have a background in this particular software. And then future in relation with this is like it's completely even with the aid of AI technologies, it could implant, we could use more of climatic models with the aid of AI. And even real-time adaptive design systems, that is the real-time monitoring can be done, or real-time analysis can be carried out with the aid of the generative system when it is accompanied with AI. And in the end, related with the conclusion, designing climate resilient cities with generative design, I would like to quote some certain points like climate risk demand new data-driven urban planning approaches. Generative designs basically enables rapid evidence-based scenario testing, and it also integrates climate, environment, and social and spatial data, and supports decision makers with optimized and resilient solutions, enhances sustainability, livability, and long-term adaptability, and path forward, capacity building, digital tools, cross-sector collaborations can be done. Cross-sector collaboration in a sense, many softwares, data could be interlinked or used up, so it can be used as an integrated collaborative platform. So that's all about today's session in regard with the generative design aspects related with urban planning, climate resilient urban planning.
Thank you very much, ma'am. We now move to the discussion session. I request the participants to kindly post their questions in chat box, or you may raise your hand if you wish to ask your question directly. Please keep your questions brief and relevant to today's topics on disaster management and resilient infrastructure on the topic.
Good evening, ma'am.
Yeah, good evening.
I would like to ask you, can you please discuss the risks of over parameterization in generative models?
Over parameterization, what actually happens up is like it loads the complete network, and sometimes the design solutions won't be, you won't get it in a day. Sometimes it might take some few more hours, and it also depends upon the memory space that the laptop or the system that you're using.
Thank you, ma'am.
Yeah.
Ma'am, there is a question in the chat box.
Yeah.
Can these tools generate drainage or road profiles optimized for extreme rain?
Yes. It can basically generate the drainage as well as the road profiles optimized, because if you're providing the road profiles data accurately, then for extreme rainfall conditions, even you have to give the what weather data accordingly. So based on the weather data for a particular location, it basically generates the road profiles as well as the drainage systems as such. Thank you, Leda ma'am, for providing a feedback. And any other further questions? If any further questions are there, you can type within the chat box, or you can just ask me as such.
Madam, good evening. I'm Dr.
Yeah.
J.T. Nayak.
Yes, sir.
Yeah, most of this time we had that during the rainy season, Mumbai is drowning sometimes. What is the reason? How can you mitigate the drowning problem?
Is it the drainage situation you are letting me know? Like, is it the drainage
Planning. What is the there is
risk?
some difference in their planning or something? Why it is drowning most of the rainy season?
Most of the rainy season, why is it drowning? It's basically of the terrain profile or the elevation, which is basically the Delhi terrain profile, which is currently over there. It's not a proper, what do you say, below, not on proper elevation is there. That's why. Second thing is that if the underground water systems are high in nature, then of course there are chances of water table is higher. Then of course there's chances of drowning. And
What
even
solution for that one?
even Delhi being highly populated, not only populated, it's also a huge pollution oriented city. So just because of the pollution effects, there can be climatic impacts, and thus leading to higher rainfall. As you could see that there are even recently the volcanic eruption that happened, it had totally polluted the Delhi scenario. So it's again going to have a climatic change. What do you say? A huge impact on the climatic sector in Delhi.
Ma'am, there is a question in the chat box.
Thank you.
How
Thank
do
you very much.
Yeah. Thank you, sir.
There's a question in the chat box. How do uncertainties in rainfall and flood models affect generative outputs?
How do uncertainties in rainfall and flood models affect generative outputs? So uncertainties, basically, it depends totally on the data that you provide. So if you are designing a particular city as such, you really need to provide accurate, detailed information related with that for around 10 to 20 years. And then I don't think uncertainties, even to to a small extent it will be there, but yeah, probably the output would be accurate. If the input is accurate, then output also you can rely on. Yeah. Actually, I was totally interested in bringing forth the software analysis because it was so curious while I was doing the masters there. So I just thought it's better to have a discussion over here. That's why I have been bring forth, even though it's not totally related with us, complete structural design analysis or geotechnical analysis. But I really wanted to uh, focus on the softwares. And in order to learn the software, it's very easy. You have complete YouTube tutorials in the YouTube itself. The basic tutorials are there, and if at all, and for designing certain infrastructures or for designing some city planning or designing some skyscrapers or domes or shells, the basic elements of codes are present in GitHub. So if you give a search in GitHub, you could get the code. Then you have to have the Rhino installed in your computer, but make sure that the computer have a much memory or the space so that this can be used, because once I was using Lenovo software, which was not it was not having much capacity. So during my project time, especially when I was doing my master thesis, so it was quite difficult for me to have the analysis done. Then I had to approach my professor and use his laptop in order to generate the complete thing. Okay, how reliable are climate projection inputs used in generative design? How reliable? That I have answered earlier itself, because if the climatic data that you provide in the climatic data profiles, you could provide it as APIs, or you can provide Excel sheets. It all depends on you. So whatever data you are implanting into it or providing into it, it provides you reliable output. And even future climatic projections can also be carried out. Like if supposedly you need to know in 2100 what are if you're designing a city in Delhi itself and you wanted to know how the rainfall impacts or the flood impacts would be, and if you're providing all the data into that Rhino Grasshopper software and then designing the entire structure and then doing the analysis, then of course you would be able to see that in 2100 how the structure would be performing. And every sort of analysis, whether it is structural analysis, whether it is geotechnical analysis, all the sort of analysis could be carried out. Even in relation with supposedly if some icons are not available, then you can provide the equations in terms of you can provide some analysis equations, or you can write it down, rather type it down within the icons. Some input icons will be there where you can type the commands, the Python commands, and carry out the analysis. And the result, either you want it in a graph format, or some bar graph. That also you can provide whatever data you required, whatever analysis output you require, that also you can provide, so based on which it will be generated. How do Grasshopper and Dynamo different handling generative design workflows? It basically depends on the extra icons or the extra climatic icons used, because in in Revit we have a particular, I don't exactly remember which one is linked with Revit. I have started my designing process in that, but I have done it some 4-5 years ago. So in that there is an embedded icon, I think it's Dynamo. So inside that we have some icons are there for climatical analysis and all, but in the case of Rhino and Grasshopper, it is far-fetched, different climatical aspects or weather conditions or disastrous, earthquake related or whatever, all the analysis could be comparatively done in Grasshopper, this Rhino Grasshopper, very fast, and it is more reliable compared with Revit Dynamo. Because while I was doing my master thesis, I have done it in Revit Dynamo first, but then just to make sure that my analysis are more reliable, then I had to switch to Rhino and Grasshopper. Thank you, sir. Thank you, Sripati sir, for providing me the feedback.
Okay, ma'am, I think the questions are over.
Yeah.
I sincerely thank you for delivering the enlightening session. The clarity of the explanation and practical relevance made the session highly engaging and informative. Thank you, ma'am, for patiently addressing all the questions, and thank you all the participants for active interaction. The feedback link for the will be available in the chat box and also in the WhatsApp group. Kindly please fill the form. The next section will be start soon. Now I request Ms. Ocean and Matthews ma'am to kindly take over the session and introduce the next resource person. Thank you, ma'am.
Thank you. Thank you. Thanks a lot. Yeah.
Nidhi ma'am. Nidhi
Hello.
ma'am, are you
Yes,
on?
am I audible?
Yes, ma'am, Nidhi ma'am. Yes, you are audible. Okay, now we are moving to second session of Day 2 FDP, and the topic is structural health monitoring for heritage structures for disaster resilience. And the session will lead by Dr. Nidhi M. About her, Dr. Nidhi M, Assistant Professor of Department of Civil Engineering, NIT Puducherry. She completed BTech from NSS College of Engineering, Palakkad, MTech from College of Engineering, Trivandrum, and PhD from NIT Calicut. She has 14 years of teaching experience in various engineering colleges. She is expert in the area of structural health monitoring, fiber reinforced concrete, vulnerability prediction model for the heritage minarets of India, and applications of machine learning techniques in the prediction of concrete properties. She also won ICA Ultratech Award 2017 for the outstanding thesis in the field of concrete. We welcome you, ma'am.
Thank you. Thank you for the warm introduction. And thank you for inviting me to be a part of this program.
Yes, ma'am. Thank you.
Shall we start?
Yes, ma'am, you can start the session now.
I'm trying to share the screen. Is my screen visible? Hello.
One
Hello.
minute, ma'am.
Is my screen visible?
Yes.
Okay.
Ma'am, can you share the presentation?
Yeah, I have shared the screen, but let
Ma'am,
me
I
check.
think your voice is not audible.
Am I audible now?
Yes, ma'am. Ma'am, can you please share? Oh, it's okay now.
Yeah. Is the screen visible?
Yes, ma'am. You are visible, ma'am. Yes, ma'am.
Yeah. Okay. So we shall start the session. So the topic of today's discussion is structural health monitoring of slender heritage structure for disaster resilience. So I'd be discussing about what is structural health monitoring in the beginning. And then we have done a case study on this. So it was on slender masonry structures. So how the study was carried out, how the field measurements, readings and all was taken, how the analysis was done. So all these will be discussed in today's session. So this is the outline of the presentation. So what is structural health monitoring? Everybody would be knowing. And then what are the steps involved in the structural health monitoring? What to be monitored, how and why to be monitored. And a short introduction about what are slender masonry structures. And then different case studies we have conducted in India. and then to the conclusion. So this is how the today's session would look like. So basically, what is structural health monitoring? So it is nothing but like if we get sick, we go to a doctor, right? So what a doctor does to a patient, similar thing a structural health monitoring engineer will do towards a structure. For example, the doctor will investigate. So first he will see what are the visual inspection we call in the structural health monitoring term. So likewise, the doctor will see you, will check your eyes and what are the mild symptoms like that he will check. And then if something is to be reported or further investigation, he may ask for a X-ray, CT scan, etc. And then by reading the X-ray or CT scan, he can understand what is the cause or what is the cause of your disease. So that is how the doctor investigates. Similar manner, a structural health monitor or an engineer also does the similar procedure for a structure. So here first step of structural health monitoring is a visual inspection. Then if some additional data are required, we will do accordingly. So basically structural health monitoring is a process of implementing a damage detection and characterization strategy for engineering structure. So damages can be due to mismanagement in the construction. As we know, there can be a lot of problem during the construction. Also due to lack of quality control. There may be changes due to temperature variation, especially in the case of hot weather concreting and all, there will be variation in temperature. Because of that, damages can occur. Then due to repeated loading or cyclic loading, there can be cracks in the structure. Damages can also occur due to the changes in the geometry of the structure or geometric property of the structure, boundary condition. For example, we design a structure to be maybe a fixed end, but due to some limitations, it may not be fully fixed. So, or whatever we design for, it may be having some changes when it is implemented. So changes in boundary condition can also affect the quality of the structure or cause damage to the structure. Then the characteristics of the system, for example, the fundamental frequency, natural frequency, mode shapes, etc. So all these can affect the structure. So why are we going for the structural health monitoring? So basically, it is to ensure safety of the structure and replace a schedule-driven maintenance with condition-based maintenance. For example, what we generally do is a routine maintenance. Like we'll put a schedule, we go for the maintenance and check the structures. But we are not bothered like whether the condition, we are not doing it when the condition is bad, or if it is routine, we'll just do that as a routine process. Whereas if we incorporate the structural health monitoring, we can assess the damage of the structure. So when it is required, according to the condition of the structure, we will do the monitoring. So because of that, we can reduce the cost based on that. And using the structural health monitoring can increase the structure's longevity. Also, we can detect the damages at the early stages, and which will enhance the whatever remedies has to be taken can be taken early. So as such, the total cost reduction can be brought down. So firstly, in structural health monitoring, we have certain terms such as system components. So what are system components? So for example, let us take the structure. So this is a slender structure. So it is a cantilever type of structure. It's a high-rise building. So we divide it into different nodes. So at different locations, we can put the sensors. Similarly, in the case of a bridge, for example, this is a bridge. Hello. Hope I'm audible. Everything is fine.
Yes.
Yes, madam, you're audible.
Okay. So somebody's mic is unmute, I guess. Yeah. So let us continue. So let us take the structure. So this is a bridge structure. So you can see different nodes. We can select different nodes. So at different nodes, we can fix the sensors. So we can continuously monitor the structure. So for example, let us consider this bridge. So this bridge, if you put like this, we are putting sensors at various locations and we can get those data, what are the changes happening in the data acquisition system. And then we can, so this is at the site. And then we can, through proper communication system or through internet, we can get into our system. So we can just simply sit in our office and monitor the structure. So then we can process the data, we can store the data as we require, and we can prepare the diagnostics. Okay, what are the changes occurring in the structure? Is there anything to be addressed immediately? So like that, we can know about the structure simply sitting at our office. So what all we need to monitor? So we can monitor the load, so changes in the load. What are the deformations happening? Strain. We can also note down the temperature. We can measure the acceleration, wind speed, pressure, etc. Then we can also monitor the acoustic emission. So some acoustic sensors we can put. We can use video monitoring. So we can also, so these are the things to be monitored. And also we can detect what are the corrosion. Is corrosion happening? What is the rate of corrosion? Is there any crack which is occurring? How the crack is growing? What is the type of crack? So all those things we can monitor. We can monitor the strength, any tension and location. Where is the distress happening? So such things we can monitor. So basically the first step in a structural health monitoring system is the visual inspection. So this is how basically what does visual inspection look like. So if there is a column, we can just go around and see, right? And if the area is very inaccessible, what we can do? In case of inaccessible areas, what we can do? Now we can go with the drones. Like we can use the drones to collect data, right? So we can see so there are some cracks here. I hope you can see my pointer, how I'm pointing. Yes?
Yes.
Yeah. So here we can see different cracks in the structure. So like that, we can take photographs. And then we can, even we can do laser scanning, drones, digital photogrammetry, etc. So these are very simple approaches, but how to read the results, that is important. So for that, we need some experience. And with this technique, we can identify the irregularities in the structure. Is there any irregularities? Are there any cracks? Any delamination which has occurred? So like that, we can monitor. Are there any discontinuities? Out of plumb? That means there is a change in the orientation. There are any cracks, damages, or even settlements in the structure. So all these can be analyzed, or some data can be taken by this visual inspection. And with this, we can prepare the detailed geometrical survey we can do. We can do the material characteristics. We can find out. So we can also, as I told earlier, we can measure strain, temperature, acceleration, wind speed, aquatic emission. So these are the equipments which are used for these. So for example, load cell. Load cell is the instrument which we can use to measure the load or forces which are happening on the structure. To measure acceleration, we can install accelerometers. Then LVDTs, linear variable displacement transducers. This can be embedded to measure the changes in the variation of displacement. Then strain gauges to measure the strain. So these are certain equipments which we can use to monitor the different parameters such as force, displacement, acceleration, strain, etc. Now, there are also some techniques such as laser test, wherein there would be a crack. We can put like a similar to a camera, like a CC camera. So like that, we can apply the laser sources there. And then there is a polarizer, and then we can process the data. We can find out what is happening inside the structure by passing this laser light. Similarly, sonic test. So you might have heard about this UPV, ultrasonic pulse velocity testing. So same procedure, that is, there would be a transducer, okay, and a receiver. Basically, two transducers are there. So there is a transmitter and a receiver. So wherein we will provide the ultrasonic pulse, and then we will receive it, and then we can measure the time taken. We can also measure the velocity. So based on that, we can find out whether there is an abnormality or a crack occurring in the structure. Then we can also use the infrared thermography technique. So similar to this laser technique, here there would be an energy source. There is a radiometer wherein the radiographic rays would be passed, and then there will be thermal radiation. Measuring this, we can detect the abnormality or crack in the structure. So moving on, we can measure static-based structural health monitoring, also dynamic. So what we measure in a static-based structural health monitoring system is that damages which alter the static properties, that is displacement, rotation, slope, etc. Whereas in dynamic testing or vibration-based structural health monitoring, so what is the difference? Dynamic properties are something which vary with respect to time, right? So, so in the case of maybe an earthquake occurring everywhere, we see this dynamic analysis. So in the dynamic analysis, the basic terms which we need to know is the frequency, time period, mode shapes, etc. So we'll discuss that. So what is when the damage will alter the dynamic property of the structure, we have to use this dynamic vibration-based structural health monitoring. For example, frequency or time period. So by knowing the frequency or time period of a structure, we can get to know the stiffness of the structure. Stiffness means like how much deformation the structure can take. So by that, we can find out how the structure is likely, or how it behaves in an earthquake and all, we can find out. So basically, frequency is nothing but number of oscillations per second, right? And then we can find out the mode shape. So mode shapes, from the mode shapes, we can find out the deformation and damping. So I'll explain this term. So damping, with respect to damping, if we find out damping, we can find out whether an internal damage has occurred or not. So we can detect the internal changes which has occurred in the structure. So mode shapes are nothing but, so when a structure vibrates, it does not move randomly. It vibrates in a specific pattern. So because of that, we can see different shapes of the movement. So these are known as the mode shapes. So if you consider a cantilever structure, we can see how it is moving, right? We can get the first model shape, second model shape, and third model shape, and so on. So these patterns are called as the mode shapes. So each mode shapes correspond to the specific natural frequency. So it is very important to know the natural frequency of the structure. Why? Because like if an external force is acting, or wind or heavy wind is acting, or seismic force is acting, if the frequency or the natural frequency of the structure matches with the wind force, externally acting force, then resonance can happen, and we know that the effect will amplify and the damage will occur. Like damage can be very drastic. So we'll be knowing about the damage of the Tacoma Bridge collapse, which happened in 1940. So there, what happened? So happened was that the natural frequency of the bridge, which that was similar or matched with the external wind which was acting in that area, and because of that, the bridge vibrated very violently, and then it had collapsed. So similar case. So in that context, we need to know the natural frequency of the structure, which is very important to know. And then the mode shape shows how different parts of the structure move relative to each other. For example, some parts may move a lot, some parts very little. So which are stationary are called as the nodes. So mode shapes are independent of external forces. So this we do this model analysis when the structure is not vibrated or with its natural frequency or natural state, we will measure the mode shape. So this depends upon the structure's mass and stiffness alone, not on the external force. So by understanding the mode shape, we can identify the critical regions which are prone to damage during vibration. And what is damping? So damping is nothing but, so there is an excitation, that excitation will die out naturally, and that phenomenon is known as the damping. So damping is a mechanism by which the vibrational energy is dissipated in a structure, typically in the form of heat, friction, or material deformation. So even when there is a heavy wind or a seismic force which is occurring, the structure will absorb that energy and then slowly it will dissipate. So that effect, then the effect will die out. So that effect, energy dissipation effect, is known as the damping. So when a structure like bridge or building vibrates due to wind, traffic, or earthquake, damping helps to reduce those vibrations over time and bringing the structure back to rest. So due to this damping, it prevents the excessive vibration which is occurring in the structure. And this protects the structure from fatigue or failure or sudden failure. So this also improves the comfort and safety, especially in the case of tall buildings or bridges. Especially in the tall buildings, the buildings will tend to sway. So if there is proper damping system, we will not feel that effect in the structure. So we will, so dynamic vibration system. So we will collect the experimental data and then the analysis of the structural behavior and the assessment of the global health state. So this can be done by using the numerical analysis, using the finite element method. So we can do the operational model analysis. So based on this mod shapes and frequency, we'll feed this, and this is known as the system identification, understanding the frequency and mode shape. Then we prepare, based on this data, we can prepare the numerical model, and then we can find out the model updating. We can do the model updating, and we can feed it into the baseline model, or which is our finite element model. And then the validated numerical model is used to determine the response of the structure under different conditions. For example, now we have created this baseline model in the finite element software. Now we can put the actual, maybe an earthquake data we can put. So we can find out how the structure behaves when an earthquake is occurring. So this will help us for the damage prediction, assessment of the effectiveness and seismic vulnerability of the structure. And then with that, we can take preventative measures or corrective action. Like, okay, so this is the natural frequency, this is the mode shape of the structure. I got that, I fed it into the finite element model. And then in the finite element model, I am putting the earthquake data. So I can predict, like, okay, when an earthquake happens, these are going to happen, or where the damages are going to occur. So based on that, I can do the preventative measures. So that is the whole idea. So this is a flow chart showing. So first we will measure the model property based on the experimental data from the site. Then we will prepare the baseline model, which is a finite element model. Then we compare, and then we will update the model with the actual case. So a baseline model is a numerical model, usually finite element model of the structure. So this is built using the initial design data, material property, geometry and boundary condition, which we can take from the site actual structure. Then so this represents a theoretical or expected behavior of the structure before any damage or alteration. Then we have this numerical model updating or model updating. So this model refers the mode shape, right? So the process of adjusting or refining the numerical model so that the predicted dynamic behavior, that is the natural frequency, mode shape, damping, matches the measured data from the actual structure. So the steps include, we will measure the model property from experiments, like by using the accelerometer, and we will get the mode shape frequency by analysis. Then compare this with the model properties of the predicted baseline finite element model. We'll identify if any discrepancies are there, and then update the model parameters. So for this case, we have taken the slender masonry structures. For example, so slender masonry structure means like one dimension is larger than the other two dimensions. So it is very tall in this case. For example, this bell tower or these columns, right, or chimneys, or these are minarets. So I'll discuss what is a minaret. So masonry minarets are integral part of architectural heritage, and they have suffered a lot of due to natural disasters such as earthquakes. So for example, we can see, so assessing the current condition of these minarets are important, and there is a need for proper structural assessment to address actual behavior of this minaret for its conservation and preservation. For example, we can see in the photograph A, we can see there is a mosque here and there is a minaret. So this minaret, so after the earthquake, so this was a picture of Turkey earthquake in February 23. So we can see that after the earthquake, this In the second picture, the minaret is not there. It has completely collapsed. Similarly, here another minaret. Okay, so this is a masonry minaret which we can see here. So this also was severely damaged after this earthquake. So masonry minarets are, so in Islamic culture, we know there is a masonry minarets are used to call for prayer, and also as a mosque, it is used as a mosque symbol. So it is a slender structure. It behaves like a cantilever. It is very sensitive to horizontal and dynamic loads such as earthquake, and sometimes it is affected by the wind or traffic. So this is how the classical minaret structure will look like. It is having a footing. There is a bottom part. There is a transition segment. This is a cylindrical or polygonal shaft. This is a body. And then there is a balcony. And there is an upper part. And there is a spiral. And there is an end ornament. So this is how the minaret will look like. So this is a cross section at the balcony level. Okay, there are stairs which through which we can access the minaret. So as part of this project, we have taken three minaret structures, that is Chand Minar in Aurangabad, Maharashtra, Julta Minar, Ahmedabad, Gujarat, and Hiran Minar in Uttar Pradesh. So these are naturally protected monuments as per the Archaeological Survey of India. So we can see the different location of these minarets. And these are like nationally protected monuments or world heritage, and there are 3,696 nationally protected monuments as per Archaeological Survey of India, and 42 World Heritage Monument sites. So these minarets comes under this nationally protected monuments. So this was the work done. So first the field documentation. So field documentation using geometrical, drone survey and non-destructive testing methods. Then preparation of models, FEM model as I have discussed earlier. Then the model was updated. So the model properties, calculations using empirical equations. Then system identification. System identifications are nothing but the understanding the natural frequency, mode shape. Then we use this for this finite element model of the structure. Then dynamic analysis. Then examine the horizontal drift and stresses in the minaret. So this was the workflow. So the first step was, as I told, the visual inspection. So for that, we did the drone-based geometrical survey. So based on this, we got the geometrical details of the structure as well. So for this, we used this DJI Air 2S drone. So this was how the flight was set. So this is a picture of the minaret. So this was the drone. You can see the drone here. Right. So this is and using this drone, we could take about 300 to 400 photos of the minaret. So this this photograph was from the Chand Minar. Okay, so Chand Minar, so these are the details of the minaret. So it consisted of an arched plinth and a tower made of local basalt. And there was plaster in the color of red sandstone. And there are different areas inside. So this is also like similar to the depicted like classic minaret structure. We can see the balcony here, and we can see the catacomb like structures at the bottom of the tower. So based on, yeah, so we can see the different layers, like the ground level, we can see. So this is a plan of the ground level. And then at the mosque level, we can see the staircase. And there is at the minaret level, we can access here and come to the minaret level. And then we can go inside and go up also. So this was the picture from the Chand Minar, Maharashtra. Then moving on to the Hiran Minar at Uttar Pradesh. So here the difference is there is a square platform at the bottom, and then there is an octagonal plinth, and then this is a minaret structure. So here we can see an interesting thing, that is, here we can see, observe closely, we can see these white color things. So this is basically, it represents the elephant tusk. So this minaret was built by Emperor Akbar. So it is said that like after each winning, this elephant tusk was used to, actual elephant tusk was used to decorate this. But at this present moment, we can see like it is like plastered, with the same color. It is some plastering which is used to depict the actual elephant tusk. Okay, and then the next structure data was taken from the Julta Minar, which is located in Gujarat. So here we can see due to the wars and all, there were like different minarets were there, but many were damaged. So we can see these are like twin minarets, and then there is a connecting central archway which is connecting both the minaret. So there was during British Raj, one of the, if you can see in this figure, this minaret portion, one portion was taken, dismantled for some studies, but it was not put back. So there was a lot of restrictions while going to take to the field and collecting data. So these are till now it is a shaking minaret, because it's this vibration at one minar and the second one, so they both move similarly. So it is the Julta means moving. So it is a moving minaret or shaking minaret. So certain minarets we can see their top tower is not there. So it could not survive the earthquake. So if you go into detail, so this monument has two vibrating cylindrical minarets. Okay, and there is a separating distance. And then we can see, so this is my PhD scholar who is standing here. He went there to take the data. And some of them was already rectified. Like we can see some horizontal steel belts over there. So some studies were already conducted. And then some retrofitting measures were already taken there, right? And these are the geometrical details. So we have the bridge here, right? So it's a twin tower. You can see the twin minarets here. And this is at the bridge level, and then at the minaret level, then at the plinth level. And there are stairs, like spiral stairs are there, through which we can access inside the minaret. So this is a part of the field documentation and non-destructive testing. So to get the material property and natural characteristics of the minaret, so since it's a historic site, we cannot take any material. For example, to find out the Young's modulus and all, we cannot take any material, or we are not even allowed to take the core, because it's actually a naturally protected monument. So it was all protected, and then we were allowed to take the UPV test, ultrasonic pulse velocity test. So we use direct and indirect methods. So you can see the equipment UPV which we use. So you can see there's a transmitter, there's a receiver. So he's taking the reading from the minaret, different locations. He's taking the readings, right? And by these readings, we can measure the velocity with which we can correlate with the modulus of elasticity of the structure. And ambient vibration testing was done. So ambient vibration testing, it's a non-destructive testing method to assess the property. So as I told you, we can measure the natural frequency, mode shape, damping ratio. So this was the instrument which was used, that is the accelerometer. And these are the different accelerometers which we use. So we fix the accelerometer at different location, and then we could get the natural frequency, mode shapes and all from this analysis. So the sensors are the accelerometers which are installed at different parts of the structure. So the vibration was recorded for a period. So here we have used this ambient vibration testing. That is, there is no external load which is not applied, like wind force, seismic load, nothing is there. It is how the structure vibrates on its own. And the vibration was recorded for a period. Then we process the data, like different location from the accelerometer reading. The natural excitation was taken, and then the model function. So we can see the frequency variation and the peaks were taken. And then from that, we could draw the mode shape. We could find out the mode shape, right? And the mode shape was found out. And so this is the operational model analysis, which is used to determine the dynamic characteristic of a structure without applying the artificial or controlled forces. So after this, and we fed this data into this finite element model, we can do the seismic analysis. Some existing data or nearby, like existing data, we can feed into the system and do this seismic analysis. And as a result, we can find out the strain, stresses, damages, and deformations of the structure, which can happen due to an expected earthquake. So like that, we can find out the details. So similarly, we can also incorporate AI-assisted inspection process. For example, for data collection, we can use a mobile phones. We can take some data, even from the drone. We can even from the webcam. We can collect data from various sources. We can clean the data, and then we can do the data labeling. That means, for example, if you see a figure, see a picture, okay, this is representing falling. So like that, we can model. And what is this figure? So, okay, this represents crack. Like that, we can train our AI model. So we can use deep learning techniques, or we can even test the data set. So this is the application. So similarly, we have done like by going there and taking. So even we can train this AI techniques and do this data collection. And then we can detect the damage classification. We can find out whether it's a crack, whether it's a spalling, efflorescence, missing components, etc. So this process also can be done. And then coming to the summary and conclusion. So structural health monitoring helps in early detection and diagnosis of a structure and the potential damages which is occurring in a structure, so that we can prevent the catastrophic failure and reducing the maintenance cost. So we can predict well ahead what are going to happen in the structure, and then we can prevent the severe collapses. So advancements in technologies such as sensor technology, data analytics, machine learning, and all can significantly improve the effectiveness and efficiency of the structural health monitoring systems. And these technologies enable continuous, we can also use the real-time monitoring, provide valuable insights to the structural integrity of the assets. So the structural health monitoring research and technology development will pave the way for more resilient and intelligent infrastructure systems. So this project was carried out with the funding from the CDRI, Coalition for Disaster Resilient Infrastructure, with the help of Archaeological Survey of India and National Institute of Technology, Puducherry. These are the selected references. Open for discussion. Any questions?
Thank you, ma'am. Thank you for the very informative and insightful session.
Thank you.
Okay, now it's the time for open discussion. So if you have any queries or questions, you can ask here, or you can post in the chat box.
Good evening, ma'am.
Yes.
I'm Anju. Actually, it was a very informative session and engaging one. So I have a question to ask you.
Yes, please.
How is data collected, stored, and processed in structural health monitoring system?
Yeah. So, as I told you, I'll just go back to the slide. So we use this. Yeah. So these were the accelerometers we used. So basically to get the acceleration from the structure. So this data, so these sensors were used and this vibration was recorded for a period. And then with the sensor, we can, if you connect it, we can directly get into our laptop, what are the data, and this natural excitation. So like something like this will come. And then we can also input in the softwares and get the details. Like we have to also do this data cleaning, all those things, and then we have processed the data.
Okay, ma'am. So is it like a resonance? The frequency response is like a resonance?
Not really, because see, resonant frequency is like if the building will have its natural frequency, right? So we are finding out the natural frequency, and the resonant frequency is something which like is then earthquake or an external wind which is occurring. So if that is matching, the resonance will occur. So if we are finding out this natural frequency, and then we can also induce earthquake data in our using our finite element model. So in that, we can detect like, okay, when an earthquake happens, how the structure is going to behave and where the damage is going to occur. So such things can be detected.
Okay, ma'am. Thank you.
Ma'am, few more questions were asked in the chat box.
Yeah, sure.
Ma'am,
Yeah,
Ma'am,
so the first one is, what type of sensors are commonly used in structural health monitoring?
Yeah. So structural health monitoring, we are basically using accelerometers. So for example, here from the company, we use this Bean Air. So this Bean device, you can see in the picture. So these are the details of the accelerometer we used from the Bean Space. So with this itself, there will be a software. So with that, also we can detect and get the data. We can even use the strain gauges and different, for example, if temperature we want to measure. So depending upon our requirement, we can use various sensors.
Okay, ma'am, thank you. Ma'am, then another question is, can SHM be applied to stone monuments of huge heights other than lime mortar slender structures?
Yes, it can be used for any structure. Yes, of course. Because basically we are finding out the natural frequency of that structure. So whatever material, so what is the Young's modulus, all those things we can get it from this. So like we can also basic property, material property we have taken using this NDT. Like you have seen, like initial slides I have shown, no? So here, this is the NDT technique only we have used. That is the UPV, ultrasonic pulse velocity. So instead of this, we can use for stone masonry structure also. So basically, this is done to get the modulus of elasticity. because we cannot take this structure or do any laboratory investigation. So we are using this UPV testing.
Okay, ma'am. Then another question. For Minar, it is very sensitive for earthquake. So what are the precautions we can take in design by considering the earthquake?
Yeah, like precautions as in like normally what we do. Like we don't, for example, it is, we have to take care like this what to say, like the codal provisions. So now the seismic zone have also been changed, right? So as per the codal provisions, we can follow, but these are like existing, like very old structures. So if new structures are there, designing, we can design using the code, but these are like heritage structures. So what we can do is some retrofitting for these existing structures. So for that, as I showed you in the figure, yeah, here some horizontal steel belts were provided additionally. So like that, we can provide a structure like some integrity, to increase the integrity of the structure. We can provide some retrofitting strategies. We can implement some retrofitting strategies to the existing structures.
Okay, ma'am. Then one more question is there. How can SHM helps in post-disaster management?
Maybe post disaster. No, basically it is used to detect early, right? Structural health monitoring, like before the disaster, how we can investigate the structure. Post disaster, maybe some data like how the damage occurred, or yeah, of course, if we are not finding out it beforehand, even that data can be utilized. Like no data is waste, right? So from that data, we can find out like, okay, at what frequency or what was the load at which the failure occurred. So all those data, we can trace it, and then which helps in maybe building up guidelines for later structures or in the future use. We can utilize those data, and some recommendations can be generated out of that.
Okay, ma'am. Then few more questions, ma'am. Then
Sure.
what role does SHM play during flood and moisture-induced damage?
Flood and?
Moisture-induced damage.
Okay. Okay, I have not investigated in that area, but still I can just, yeah. So moisture induced means if you detect some damage, like we can see what is the cause of the damage, we can find out. And then if it is moisture induced damage, means what can be precautions, what we can do. So such things can be done. What is the actual question? Like,
Ma'am, what role does SHM play during flood and moisture-induced damage?
okay. So yeah, moisture induced damage is there, means we can detect, like, for example, we can find out what kind of, what is the extent of damage. So like that we can find out. I don't know, like I'm not an expert in flood induced SHM. So maybe some other experts can take up
And can I ask a question?
that. Yeah, sure.
Myself, Dr. Swail from NIT Srinagar. I have a question.
Sure.
Of a colleague of mine is working over this, carbon fibers. He is working on a carbon fiber. So he has introduced the strain gauge placement in the lab.
Okay. Yeah.
Loading, trying to evaluate the results. So he's trying to connect it with the some structural health monitoring. Now the
Okay.
question, question that I arise, though I'm not much, maybe this question is different from my field, but as an observer to this seminar, or we could say FDP, I just have a question in mind that I want to put forward.
Sure.
When I see the strain gauges, when we are incorporating it within the concrete at the times, and we say sometimes also placing it over the reinforcement so that we can get the signals for the data acquisition system. Now the question that arises, however, in case of the ancient structures or the already structure that we have built, we are trying to switch towards the sensor that we place it over the surface for acquisition of the data, because it's that time it's not possible to embed within the concrete. The question is whether the environmental disturbances like the noise or the sound system, or sometimes the disturbances caused by the environment, do they have an impact over the data acquisition or the SHM data? Or in order to overcome this, though we have developed an advanced filtering technique in this field, or that is still another question, ma'am.
Yeah, actually, as you rightly pointed out, like if there is a heavy traffic in a nearby region, that can affect the data, obviously. So what we can do is we can fix some timing wherein, like, obviously there will be some noises, there will be some disturbances, noises would be there. But from the data, we can filter out that to an extent. And beyond that, like while taking the readings also, we can take during the like non-peak hours. So like that, if you take, we can naturally reduce the disturbances. So that is the only thing we can do at this point. But like as you rightly pointed out, it is like we cannot embed it inside, right? So it is an externally only we are putting, but we can like the noises we can clear out. Like we can filter out the unwanted disturbances in data cleaning process. We can do that.
Later on, the data acquisition, the data that we have filtered can be integrated with the machine learning or the AI system, and we can get the results as per the desired. Huh?
Yes, we can do that.
Presentation was very good, and it was very presentable in a very good manner, ma'am. Thank you so much.
Thank you. Thank you so much.
Excuse me, ma'am.
Yes, please.
Can you please infer in like how an SHM systems can be effectively integrated into existing bridges and buildings without major structural modifications?
Yes, here also we are like we have just like places accelerometers at different locations. So similarly, we can incorporate in the existing bridges. So here we did only for a particular period of time. So for example, if I can go back to the slide. Okay. So here we have placed the accelerometers at these locations. You can see that. Like here and here we have put the accelerometer. So similarly, so this is for a minaret structure. Similarly, we can do it for a bridge structure, right? So this can be, so this was permitted only for a few periods. We wanted to take the data for a certain period. Similarly, like this, we can attach to the bridges externally. We can do that. That is not an issue.
Thank you, and thank you for your clarified answers.
Thank you.
Ma'am, there is another question is there. What criteria should be followed for optimal sensor placement in large scale structures? What criteria should be followed for optimal sensor placement in large scale structures?
Yeah. So basically what we can do is like at different floors we can place, and we cannot spend too much on sensors also, right? So for that at each floor, each set of sensors we can place. So there is no particular method to do that optimization. But generally, with our whatever data of the structure we have and how we have to take, we can do that. That is, I don't think there is an optimal procedure for that.
Okay, ma'am. Another question is there how we done forensic audit, how to do post damage or collapse structural audit.
Okay. Yeah. So like forensic engineering also, it's like a separate, like exactly a different area itself by its own. So forensic investigation involves like first visual inspection, then NDT methods, all those things are there. So after the damage has occurred, uh, like we can inspect like what is the extent of damage we can do, or what can be done, like can it be retrofitted, or whether some repair can be done. So all those things can be done at the like after the damage has occurred, after going to the site we can get those data and do accordingly.
Okay, ma'am. Then the other one is, what are the major challenges in implementing SHM for heritage and old structures?
Yeah, basically, we cannot like if it is like an very new or any other structures, we can take the core, we can take the core and then test in our laboratories to get the properties. However, for this heritage structure, we cannot do that, like the exact material property and all. We have to do this, depend on this non-destructive testing methods for that. So that was a challenge, and also there was a lot of restrictions, like going there, taking data, and even we had planned other buildings as well, like Qutub Minar and all was planned, but we could not get access. And then, like even these buildings, we got the access through the Archaeological Survey of India only, the Archaeological Department only. So all those things are like very challenging. Like if it is like some collaborative projects and all, we will get more access. Otherwise, it is really difficult to get into the sites, because like there are cases where people are trying to damage the structures also. So like the authorities will definitely like take care of that. Like, okay, and if you do any monitoring techniques also, whether that will cause any further damage to the structure and all, they will see. And for example, in one of the examples I showed in the Julta Minar, like one part of the minaret, like that was taken for the study earlier during the British Raj period. So during that, they have taken what is happening. So they were curious to know, and then they have taken, but they could not put it back. So all these things are there. So because of that, it is really a little bit challenging to do on these structures.
Okay, ma'am. Two more questions are there. How reliable are AI and machine learning based SHM systems compared to traditional methods?
It is truly dependent upon the data we input. So if the data is proper, that is fine. And it depends upon the, like, as we tell, no, like, what is we put, that is what we get also. So it depends upon the data and the extent of data, with the variety of data we are putting. So it is like that, like it basically based upon the data only. So we cannot like, but still, if there are also models where we can use using AI techniques, but it still requires further research in that direction. Any other question?
Yes, ma'am. What are the cost-effective SHM solutions suitable for developing countries like India?
Yeah, this strain gauges and then accelerometers, all these things are not very expensive. Like all these things we can implement, like strain gauges, accelerometers, etc., can be incorporated.
Okay, ma'am. Then how extent the SHM contributes to the structural design, which provides isolated under landslide and mud flow conditions?
I have not explored in that area. I'm not an expert in that, like landslide, all those.
Okay, ma'am. Whether the data we are taking will affect the external factors, did we need to consider that?
I hope I have answered this question that, like in case of the traffic data and all, if it is there, no? So some external factors. So for that, basically, what we can do is take the data while it is like no much external disturbances are less. So that is how we can lessen the effect.
Okay, ma'am. I think all the doubts are over. Anyone have any doubt? You can ask now. If anyone having any doubt, you can ask now or kindly request to put in the chat box. Okay, ma'am. Okay, ma'am. Thank you once again. And
Okay, thank you.
yeah, and you patiently cleared all the doubts of the participants. And I hope your presentation was highly informative and beneficial to all the participants. Also, we are truly grateful for your time and effort, ma'am.
Thank you.
Thank you, ma'am.
And it is really nice of you to conduct like courses like this, so which will be helpful for all the participants. Congratulations.
Thank you, ma'am. Okay. Okay, dear
Thank you.
participants, the feedback link of session 2 will post here in the chat box as well as in the WhatsApp group. So all of you kindly fill it and leave the session. So all the sessions of day 2 FTP is over here, and thank you all for the participation, and see you all tomorrow.
All are requested to leave only after filling the link, feedback link. Are requested to leave only after filling the feedback link. You are requested to leave only after the filling of the feedback link.